So now we come to our fourth and final way of doing electron configurations. The first, of course, was the orbital notation with the boxes and the arrows. The second was the electron configurations, where we started at square one and we wrote down every energy level and sublevel and how many electrons it had in it until we got to the element's placement on the table. Then we learned that you could replace all the inside portions of the electron configuration with a noble gas element on the row above it. The nearest noble gas notation, also called compressed or condensed electron configurations. And now we come to maybe the shortest and fastest one of them all. Again, these electron configurations, whichever type we're talking about, is trying to illustrate where electrons are so that we can try to understand what the element is going to do chemically in order to be left with a stable octet, which means that it's going to be left with a filled S and filled P sublevels. Whether it loses electrons to be left full or gains electrons in order to end up full, it all involves electrons in the S and P sublevels. So Lewis dot diagrams kind of gets right to the heart of the matter. Lewis dot diagrams are ways of representing where electrons are, the valence electrons are in an atom. It gives us a picture of how many valence electrons the atom has to enable us to predict how it will behave chemically. We know that elements react chemically in order to satisfy the octet or duet rule. Lewis dot diagrams make it very easy for us to see if it's achieved chemical stability by satisfying the octet rule, because Lewis dot diagrams show the valence electrons. It shows only the electrons in the outermost S and outermost P sublevels. The S sublevel holds 2 electrons because it's made up of one orbital. The P sublevel can hold 6 valence electrons because it's made up of 3 like orbitals. So the S holds 2, the P holds 6, that gives us 8. Once again, the octet rule is dealing with the S and P's, and that's what Lewis dot diagrams focus on, the electrons in the S and P. For the smaller atoms, hydrogen, helium, lithium, they only need 2 to fill up that first level. Well, the Lewis dot diagrams are also useful in showing us how those elements can go about getting the 2 they want to be left with. So Lewis dot diagrams show valence electrons only. Valence electrons will always be in the S and P because of Aufbau's order of filling. Valence electrons can never be in the D or F. Just as a reminder why. Electrons will go into the 4s and then go back and fill the 3D. So the outer level is going to be the 4s and when the 3D is being filled. And once again, it's because the energy depends not only on the first number, this number in front, 4 and 3, but it also depends on the sublevel. When you're in the S sublevel, your second quantum number is a 0. The energy depends on the first quantum number n added to the second quantum number. So the 4s would have an energy of 4, which is the n. And when you're in the S, your L is 0. 4 plus 0 is 4. The 3D actually has a higher energy than the 4s. The 3D has an energy of 5. Why? When you're in the 3D, your N is 3, but when you're in the D, your L is 2. 3 and 2 is 5. So electrons for any of the elements on this row right here, the fourth row, the fourth period, the fourth shell, the fourth level, whatever you want to call it, any of these elements in this 3D right here would actually have valence electrons in the 4s. So valence and after the 3D is full, we then go and begin filling the 4p. So the 4s gets some, then the electrons go back to the 3D, which is inside, and then back outside to finish off the 4p. So valence electrons will always have to be in the S and the P, never in the D, and certainly valence electrons couldn't be in the F, because if you remember, The 4f doesn't even get filled till electrons are in the 6s. So elements that are in the 4f actually have valence electrons out on the 6th level. The energy of the 6s, remember when you're in the s, your second number is a 0. 6 plus 0 is 6. The 4f, the first number n is 4, and we're going to add it to the L value when you're in an f, which was 3. When you're in the f, your second number is a 3. 4 plus 3 is 7. So these elements here, number 58 through 71, in the 4f, their valence electrons are already way out on the 6th level. So the whole point of this was to remind you that valence electrons can only be found in the s and the p. That doesn't mean that those are the only electrons that can get involved in chemical reactions, but they are usually the first ones in the chemical reaction, the electrons in the s and p. So when we're doing Lewis dot diagrams, we focus on the electrons in the s and p. How many electrons would we be talking about having to focus on? Well, the s sublevel, part of our valence, only has one orbital holding 2 electrons. Remember, there were 2 columns in the s part of the table. The s holds 2. There were 6 columns in the p part of the table. The p holds 6 electrons. It's made up of 3 orbitals, each holding 2 for 6. So the Lewis dot diagram would have to have a way of showing the 4 orbitals, the 1s orbital and the 3 p orbitals, and would have to be able to have a way of showing 8 electrons. So here's what Lewis came up with. When they do a Lewis dot diagram, they write the symbol's name. The 4 sides around the symbol, the right side, the bottom, the left, and the top, represent the any of the 4 orbitals. It turns out that they've assigned the right side of the symbol. So you write a symbol. The right side's the s orbital. The bottom side of the symbol represents the p orbital. The left side's the other p orbital, and the top is the other p orbital. So our 3 p orbitals are here. Our s orbital is there. That's how they decided to represent where the orbitals were. Much different than we saw in many of the other ones. In the orbital notation, they drew boxes or lines to represent the orbitals. In electron configurations, they didn't even really represent the orbitals. They just told you how many electrons were in the sublevels. In the nearest noble gas, it's a shortened version of the electron configuration, so it's much of the same. Here, they're doing it entirely different. This side's the S, this is a P, this is a P, this is a P. Now, to represent electrons here, instead of using arrows like they did in orbital notations, they put dots in. And you have to still follow Aufbau's order of filling, which would say that the lowest energy level sublevel gets filled first. Well, the S has a lower energy than the P, so we would have to fill the S side first. Hund's rule says that each of the orbitals get 1 electron before we pair them up, so we have to follow that as well, which gets us to the order of placing electrons. Since this is the S side, the first 2 valence electrons would go here, number 1 and 2. That would take care of Aufbau. If we put 1 here and then put the next one here, that meant we didn't fill the S before we started filling the P. That would break Aufbau. Hund's rule says each p orbital gets 1 before we double them up. So the 3rd electron goes here, the 4th goes here, the 5th goes here. Now, once we've got 1 in each of the p orbitals, we can then begin doubling them up. So 6 would go here, 7 would go there, 8 would go there. Pauli exclusion principle really isn't illustrated using Lewis dot diagrams. And the other half of Hund's rule isn't really illustrated using this, because the second half is talking about in a given, if we have 1 electron in each of the p orbitals, they spin the same way. Well, here we're just drawing dots. We're not drawing arrows with spins. So how do we do Lewis dot diagrams? First, you write the symbol. Then you find the element on the periodic table, and you use the information on the periodic table to help you determine how many valence electrons it has. Determining valence electrons for the main blocks, that's the S block and the P block. The main blocks are the elements that are found in the first 2 columns to the left or the 6 columns to the right. They are very easy to do dot diagrams for. Why? First family has 1 valence electron in the S. You'd put 1 dot on this side. The second family has 2 valence electrons in the s. They're the s2. So you would have 2 on this side. Then we get to that first column in the p. They would have 2 in the s, 1 in the p for 3 dots. So they would have the 1 and the 2 and then a dot down here by the 3. Group 14, the fourth column in the main block, the second row or second column of the P. They would have 2 in the S, 2 in the P. So we'd have 1 here, then number 3 would be there, 4 would be there. Group 15 has 2 in the S, 3 in the P. So they would have 1 here, then number 3, 4, and 5 would have dots there. Group 16 would have 2 in the S, 4 in the P. So they would have number 1, a dot there, a dot where there was a 2, a dot where there's a 3, a dot where there's a 4, a dot where there's a 5, and then a dot where there's a 6. 17? Well, you're starting to get the hang of this, I hope. Really, if you remember, there were Roman numerals above each of these groups. And the Roman numerals in those groups were telling you how many valence electrons they are. Everybody in this first column would have 1 valence electron, they would have 1 dot. Everybody in this column, the second column, they have 2 in the S, so they would have 2 on the S side. Everybody in this column right here, as we mentioned, the S2P1 column, they were Roman 3. They have 3 valence electrons, 2 in the S, 1 on the P side. This group right here, group 14, would have 2 in the S, 2 in the P. So 2 here, 1 in this S side, 1 on that S side, according to Hund's rule. Group 15, Roman 5. We already know that Roman telling you how many valence electrons. 5. 2 here on the S side. Spread them out, 1 on each side for the 3 electrons in the P, 2 in the S, 3 in the P. Group 16 had the Roman 6. For the main Bach families, those Roman numerals are telling you how many valence electrons they have. This group right here has 2 in the S and 4 in the P. 1, 2, 3, and now the fourth one starts doubling them up. Group 17 is Roman 7. That 7's telling you 7 valence electrons. 2 on the S side. First one in the P goes here. Second P here. Third P here. Start doubling up. Fourth P here. Fifth P here. That's 7 dots. And finally, everybody underneath helium. Roman 8. 2 in the S, 6 in the P. 2 on each side. Octet rule is full. When you have 2 on each side, you do not want any more electrons. You are chemically stable. Now, in the case of helium, it's chemically stable with 2 because the first level only has 2. You see, the first level on the periodic table only has 2 elements, hydrogen and helium. So helium would only get 2 dots. That's all it needs to be chemically stable. Now, this is a little bit different than the transition metals, which are the D block elements, and the intertransition metals, which are the F block elements. Because remember, they fill the S, then go back and fill the D. So the ones in the Ds are not technically valence electrons. So these Roman numerals above the D block are not telling you how many valence electrons they have. Instead, they're telling you how many are in the S and the D in general. S2D1, that's a Roman 3. S2D2 is a Roman 4. S2D3 is Roman 5. S1D6 is Roman 6. 2 and 5 is 7. 2 and 6 is Roman 8. They're telling you how many's there. There's an 8 here and an 8 here, if you remember, because cobalt and nickel behave like iron. And then we get copper, whose D is now full with 10, so they go back to Roman 1. No sense in telling you how many's in the D if it's full. Zinc is S2D10. Its D's full, so there's no sense in telling you how many's in the D, so they give you a Roman 2. So how many electrons do you dot? The answer is, how many do they have in the S? We don't care how many's in the D. This one has 2 in the S. This column here generally has 2 in the S. They get 2 dots. These guys have 2 in the S. They get 2 dots. These guys have 2 in the S. They get 2 dots. Chromium has 1 in the S. It gets 1 dot. Manganese has 2 in the S. It gets 2. 2 in the S. It gets 2. 2 in the S. It gets 2. Nickel, 2 in the S. It gets 2. Copper, 1 in the S. It gets 1. Zinc, 2 in the S. It gets 2. You don't dot the D's because D's are not valence electrons. In our next video, we'll do a couple examples of dot diagrams.